In 2022, a United Nations agency report revealed that the world is heading towards sand scarcity. This surprised many, as sand is the most abundant material on Earth. It can be found anywhere, from riverine areas to dry deserts. So, how are sand reserves dwindling? According to some estimates, sand is the most extracted material on Earth. Annually, around 50 billion tons of sand are extracted worldwide. Almost every major building material, whether concrete, asphalt, or glass, is composed of sand. We use sand in paint, toothpaste, windshields, silicon chips, and nearly every essential product without which the modern way of life is impossible. Sand can be white, black, pink, red-orange, white-gray, or light brown. There are more than 20 types of sand. One of the most important types is silica. It is used in almost every glass-making product and primarily occurs in the form of quartz. Explosives are used at mining sites to extract silica. The blasted sandstone is collected with wheel loaders and then transported by dump trucks to the crusher line. There, the sandstone goes through various crushers to achieve the desired particle size distribution. This is the McClanahan jaw crusher, which acts as a primary crusher for sandstone. It consists of two opposing jaw dies that create a V-cavity called the crusher chamber. The material is squeezed between the moving jaw die and a stationary jaw die. The discharge opening controls the desired product or yield. Typically, the mined ore is reduced by a jaw crusher to about 1 inch in size. Likewise, sandstone falls on the high-speed rotor drum in the impact crusher, which breaks upon impact. The material then encounters a series of anvils or curtains that further crush it as it travels through the crusher. The crushed sand is still not pure silica. It needs to be graded and purified. For this purpose, CDE Group, a renowned company that manufactures wet processing solutions, has designed this silica sand wash plant, which can produce 220 tons of glass sand every hour. The process begins at the feeding system, where dump trucks unload the crushed silica straight into the feeding system. This system regulates the feed to the wash plant. Next, the sand goes through a pre-screen which removes the oversized material with the primary cut at 7 mesh. The term mesh refers to the number of pores per inch. For instance, the 5 Infinity high-frequency Infinity screens cut sand at 30 mesh, meaning these screens have 30 openings on every inch of their screen. Upon vibration, sand particles of a certain size can only pass through these openings. In this way, the coarse sand is separated out and stockpiled for coarse construction use. This refined silica sand now has to go through attrition cells. These cells clean the surface of particulates, removing unwanted contaminants, impurities, and pollutants. This process includes removing clay slime and cleaning surfaces of soft or conglomerate impurities. Likewise, heavy metal contaminants are removed by the spirals. The slurry rotates due to gravity and the shape of the spiral shoots. The spiral motion tends to push heavier particles inward because of centrifugal force. At the bottom of the spiral, separator gates are installed at different radii. They simply lead the slurry with the heaviest metal into different chambers and the filtered silica into another. Next, the wet, high-intensity magnetic separators further purify silica from ferromagnetic elements by attracting them with their magnetic field. Then, the feed enters the hydrocyclone, and centrifugal forces push heavier solids outward, leaving behind concentrated particles. The vortex finder creates a swirling motion, and the fluid exits through the overflow, while solids exit at the bottom. Throughout the process, water usage is optimized with the AquaCycle thickener, which recycles 90% of the water, reducing waste and environmental impact. This comprehensive process ensures the efficient production and utilization of silica for various industrial applications. The silica, ranging from mesh 30 to 100, is considered ideal for making glass. There are two famous methods of glass making: float glass processing and the glass blowing method. In the float glass method, molten glass is floated on a bed of molten tin to create a uniform thickness and smooth surface. On the other hand, the glass blowing method is employed to blow air into the molten glass to shape it into the desired form. But first, to produce glass material, silica needs to be melted at a high temperature. For this purpose, tons of extracted and purified silica are brought to the batch house. A batch house is a place where silica and all other necessary ingredients are tested. They may include soda, lime, and aluminum. Soda lowers the melting point of glass compounds, lime enhances their stability, and aluminum makes them tougher. These ingredients are then mixed evenly in a specific proportion to make a specific type of glass. For manufacturing float glass, broken glass can also be used. The recycling of wasted glass is known as cullet recycling. It is also mixed with batched material, which saves up to 15% of the new raw material. Next, the fully batched material is fed to a large furnace. It melts down the glass material at a temperature of up to 3,000 Fahrenheit, and the compound transforms into a several-foot-deep pool of liquid glass after approximately 36 hours. This liquid glass is spread over molten tin at 2,000 Fahrenheit in a separate section. The underside of the glass floats onto the tin in the tin bath and is heated from above to form a seamless sheet of glass, usually called a glass ribbon. This process is called the tin bath. To ensure the quality of the glass, each process is monitored by the manager and his team from the control room. Next, the formed glass has to go through another process called annealing. Annealing layer is a long, tunnel-like furnace with individual oven sections. There, the glass ribbon is gradually cooled down and has to pass through a pair of water-cooled forming rolls to give it a uniform thickness. At the end of the layer, the air is battered on the produced glass, further cooling it to the point where it can be cut. In the US, Cardinal FG Company produces 600 tons of float glass every day. From the main furnace to the cold end, they process 20 miles of glass ribbon and use advanced technologies to make their product defectless. Cameras detect uniformity in the glass, lasers point out any anomalies in the edge of the glass, and experts do manual inspection. If any defect is detected, that portion of the glass ribbon is automatically marked and later cut out. A special device, the XY cutter, marks a thin, continuous scratch from one end of the other edge on the surface of the glass. This process is known as scoring, which offers controlled glass fracturing along predetermined lines. While going through a bump roll, the scored ribbon splits apart or is cut into pieces of glass sheets. The edges are then trimmed. If the glass's edge remains untrimmed anywhere, the laser technology detects this defect. The defective sheet is sent back to the batch house for recycling. Finally, the ready glass arrives at the packing station. Great care is taken to package, wrap, and label the orders. Float glass manufacturing methods can only offer glass in the form of flat sheets. The air is blown from inside to transform glass into a specific shape, such as bottles, jars, or any other shape. This is why it is called the glass blowing method. More or less, the batch mixing and melting of glass in the main furnace are the same as what we have seen in float glass manufacturing. The difference in the process starts with the glass forming process. In this process, the molten glass is fed into narrow canals, which are known as feeders. The molten glass, in specific amounts, is allowed to fall through an opening at the bottom of the feeder. This falling molten glass is known as a glass gob, which is poured into black mold. The gob adapts to form the neck of the bottle due to its molten state. Next, compressed air is blown inside the molten gob to shape it according to the mold. This initial shape of the bottle is known as parison. Next, The parison is flipped to an upright position to give it the final desired shape. The injection of more air fully defines the shape. This method of glass forming is known as the blow and blow method. It is suitable for bottles with narrow necks, such as those that are used for containing beverages and perfumes. For wide mouth glass vases, the press and blow method is the industry standard. The molten gob is dropped into black mold, but before blowing it from beneath, plungers press the blank shape. This action results in the parison, or initial stage, of a glass jar. Next, the parison is transferred to another mold called the blow mold. There, compressed air is blown to give them their final shape. Glass bottles are not done yet. They need to be annealed. For this purpose, they are slowly reheated and likewise gradually cooled down. In the next stage, every glass bottle is inspected using an automatic check system or by experienced employees to ensure the quality of the final product. One by one, everything is checked, whether it is the split finish, or wall thickness of the glass bottles. Any rejected containers are immediately removed from the production line, recycled as cullets, and used in the fabrication of new glass. Interestingly, glass is the only packing material that can be totally recycled indefinitely, although the packaging bottles themselves must be carefully wrapped before shipment. Every pallet is covered with plastic wrap to protect the glass containers. Since 1984, Rotel has been manufacturing glass packaging products. With its 8 production lines, this company produces a total of 700,000 bottles and jars every single day. This glass bottle manufacturing industry reached a value of $38 billion, and it is likely to grow much more in the future. But there is another unnoticed glass product that is much smaller in size, but has globally exceeded the $8 billion market size. It captures our memories, and we use it on every other device, from smartphones to laptops, and on almost every photography gadget. It is the camera lens. An optical lens is the eye of the camera. It captures light and passes it on to the camera's sensor, thereby determining the sharpness, depth of field, and overall aesthetic of the image. Fundamentally, there are 2 types of camera lenses, the prime lens and the zoom lens. The prime lenses have a fixed focal range, while a zoom lens is made of a set of lenses that can zoom in and out by physically adjusting the focal length. Most of our flagship smartphones come equipped with zoom lenses, but the difference is that these lenses cannot slide. Instead, they seamlessly switch to the other camera with higher magnification. Whether it is a single lens or a collection of lenses, manufacturing them is way more complicated than just making float glass and glass bottles. It starts with making the perfect slab of optical glass. This isn't just any glass, it's a material chosen for its unparalleled clarity and purity, essential qualities for capturing crisp images. These glass slabs are first analyzed meticulously and then marked and cut into pieces. The resultant is known as glass blanks. Now, it needs to be transformed into a transparent optical lens. For this purpose, experts and machines work side by side. They place a blank glass or glass disc on a rotating device where a curve generator can grind it with precision. The curve generator has a diamond cutter that carves out the lens with precision using CNC technology. To transform a blank into a convex lens, it grinds the edges to make them thin, while the center remains thick. On the other hand, a concave lens is shaped by seamlessly grinding from the thin center to the thick edges. This is called spherical grinding. In the next stage, precision machining further refines the lens. Then the finely ground lens is fixed in a metal shell for future processing. This locking is called blocking. Now the lens is ready for transformation from opaque white glass into a glossy, transparent lens. To do this, factories use liquid abrasive materials such as graded emery flour and fabricated plates. This polishing process makes the lens surface smooth, transparent, and scratchless. Glass polishing is a slow procedure that requires lenses to be oscillated back and forth against a spinning polisher for hours at a time. The lenses emerge from this process with a gleam, their surfaces smooth and their profiles perfectly curved. After 3 hours of receiving this protective finish, the lenses are cleaned to remove any residue. Each lens, whether concave or convex, undergoes a rigorous inspection and cleaning process. The stakes are high, as even a single speck of dust could compromise the optical system, affecting the image quality. Next, the lens edges are coated with black ink. This ink blocks the light coming from the edges and eliminates internal reflection. The lens is now ready to be installed in the camera lens frame. Moreover, protection, anti-glare, and other types of coatings are also applied to camera lenses. Chromatic aberration is a common problem with camera lenses. It happens because a lens fails to focus all colors on the same point. To eliminate this distortion, lens manufacturers join a concave and a convex lens together. A technician applies optical cement to a convex lens and positions a concave lens on top. The application of pressure ensures the cement spreads evenly, bonding the two lenses together. This union is crucial as it stabilizes the lenses within the lens barrel, preventing any unwanted movement. The lens barrel itself is the final piece of the puzzle. A technician carefully engraves technical details onto it, such as focal length and aperture size. These inscriptions are not merely decorative. They provide photographers with essential information, enabling them to manipulate the lens to capture the desired image. As the process concludes, the individual components of the camera lens come together, each playing its part in the grand design. The end product is a tool that not just records photographs, but also captures moments in time, allowing tales to be shared and memories to be remembered. It's a testament to the skill and dedication of those who work in the shadows, their craft enabling the magic of visual storytelling to unfold before our eyes. The use of light and lenses to capture images dates back only 2 centuries, despite the fact that many civilizations in the past have used light to communicate. Narinder Singh Kapani saw the magical potential of glass for the effective use of light in transferring tremendous amounts of data across the Earth within microseconds. His published research work gave us a new breakthrough invention made of glass, optical fibers, and the brilliant man himself is renowned as the father of fiber optics. Inventing something capable of changing the world is one thing, and starting its mass production is another. An optical fiber typically consists of a core and a glass tube in the center through which light transmits. The core is covered with cladding to protect it. The first step in manufacturing optical fiber is the creation of solid glass tubes. It is called preform. This tube is rotated on its axis and heated to around 1500 degrees Celsius. At the same time, ultra-pure chemicals are put into the preform, which, when heated and contaminated with glass walls, turn into microscopic particles known as soot. These soot particles begin to adhere to the interior walls of the tube, generating a thin film. Layer by layer, the process continues. This inner layer later becomes the core of the optical fiber. After these layers are deposited, the temperature is increased and the feed of the chemicals is reduced to produce a solid rod or preform. Now, the ready preform needs to be analyzed to measure its refractive index. The refractive index indicates light bending ability through the glass medium. Germania increases the fiber's refractive index, whereas boron decreases it. The preform is now ready for fiber drawing, which will transform into optical fibers. It is lowered into a high-purity glass furnace. 1900 Celsius metals down the tip, and gravity pulls the molten tip to free fall. Following that, a thin tube with a 125-micron diameter is drawn. A diameter gauge system with laser technology ensures every bit of the optical fiber has the same desired dimensions. The optical fiber is then run through dye, which applies a protective coating to make it resilient and easy to handle. Now, it can be wound on a drum. It passes several tests and trials, such as testing tensile strength, which should be at least 100,000 per inch, and measuring its loss of optical power, carrying capacity, and numerical aperture. In recent times, scientists and engineers have discovered another hidden use of glass. A piece of transparent fused silica can store a large amount of data. Not only that, but this data on the layers of silica can last for over 300 million years. Hitachi is the pioneer of this technology. They started working on it in 2008, and after years of hard work, they managed to develop the femtosecond pulse laser equipment. This high-output laser stores data in the form of 2D code by inscribing dots on a layer inside fused silica. With an optical microscope, computers can read and retrieve the data. Hitachi claims that it can store and retrieve data on over 100 layers of an inch-thick silica piece. Microsoft is another company striving to achieve the true potential of glass in storing data. The company initiated Project Silica with the aim of inscribing data on glass in the form of voxels, or three-dimensional pixels. They even created a glass library to store those glasses. There, they have special librarian robots that will handle these crystalline archives. These were some of the wonders of glass. Since prehistoric times, mankind has been using glass, and it is still continuing to offer more. Hope you find this documentary informative. Share your thoughts in the comments, give a like to this video, and we'll see you next time.